Alrighty, so we're going to continue talking about work by introducing what's called the work-energy theorem. If you remember, work was force times distance, where this was a special type of multiplication which basically says take the amount of the force, or the component of the force, which is in the direction of motion, and multiply it by the distance traveled by the object. And that tells you how much work is done on the object. And so what we found was basically like saying the parallel component of the force to the distance. You know, if you know the block slides in the x direction, then you only need the x component of the force. If the block slides along the ramp, then you only need the parallel component of the force, and so on. But if you notice, every time we talk about this, we're applying a force to an object, and the object's moving. And we know in normal life, when you're pushing on something, you get it to move. Generally speaking, you speed it up or you slow it down. Of course, you can push with a very, very special force for that situation, which just causes the object to keep going at constant velocity. That's just, you just barely overcome friction. Or if you add up all the forces acting on the object, they all cancel out, and so there's no net force. Then it doesn't accelerate. But if you apply a force, some net force, the object's going to accelerate. And when we say it accelerates, we say the velocity of the object changes. So in working physics, the idea of energy came into play. Energy is a concept that was invented. It's kind of an abstract idea because there's no such thing as energy that you could go measure necessarily. You can't take a beaker, fill it with this energy liquid, and figure out how much it weighs, or figure out the volume of the energy, or anything like that. There's nothing you could go get that you could pick up, collect, measure, see, feel, that's energy. It's something, some characteristic of an object or a system that is there and can be calculated, but it's kind of like a made-up idea. You're not going to go open up the object and find its energy. It doesn't work that way. But it's useful because if we allow this concept of energy to exist, there's actually a very powerful technique of solving physics problems using energy. And that's what we're going to start introducing right now. When we talk about energy, we're going to say there's two types of energy. First type is called kinetic energy. And this, of course, is the energy of motion. So anytime, I'm going to refer to systems, but of course, that can also mean just an object, like a box is a system, or a person is a system, whatever. Anytime a system is moving, it has some velocity, some speed, then it has some kinetic energy. There's some energy, whatever this energy thing is, that's associated with its motion. That's what kinetic implies, of course. Well, the equation that allows us to calculate how much of this kinetic energy is stored in the system because of its motion is kinetic energy equals 1/2 the mass of the object times its velocity squared. So mass, velocity. So we can see that the kinetic energy obviously depends on the velocity. The faster an object moves, the more energy is associated with it. But we can also say that the heavier an object is, the more massive it is, the more energy it has as well. So you can have a big train moving down the train tracks going 5 meters per second. That's going to have way more kinetic energy than, let's say, a tennis ball being thrown at 1,000 meters per second. The tennis ball is definitely moving a lot faster than the train, so it's going to have a good amount of kinetic energy. But the train, being so extremely massive, even though it doesn't move as fast, can still have a higher kinetic energy. But definitely the velocity is more important to the calculation because it's v squared, so that raises the energy faster. Another thing we need to know is the units. Of course, we always care about units because when we're stuck or we don't quite know what to do, generally speaking, units can help us out. So if we look at this equation, this is kilograms for the mass. Of course, 1/2 doesn't have units. That's just a number. Velocity squared is meters squared per second squared. Right? Meters per second quantity squared. And if we look at these units, if you remember, that's just joules. So the unit of kinetic energy happens to be the same as the unit for work. It's a joule, kilogram meters squared per second squared. Or a Newton meter is the same thing, but joules. So that's good. That also hints about what we're going to be doing. Because if you have that physicsy mind or that scientific mind, you're already thinking, before you even worry about what it actually means, that wait a second, if work has the same units as energy, then we can set up an equation between the two. Because remember, the rules for equations say the left side of the equation has to have the same units as the right side of the equation. So if I already have work has joules as its units and kinetic energy has joules as its units, they could go on either side of the equation, any side of the equal sign. So that's a hint. Pretty soon we're going to say work is equal to kinetic energy in some way, maybe with other numbers involved or something, but we're going to be relating the two. We'll see how to do it, but just keep that in the very back of your mind. And also, try to think in this way. When you're learning new things, you're learning new ideas, whether it's in physics or something else. When you see something that's related between two ideas, make note of it because it might be important. But for now, just let that be. So that's one form of energy, kinetic. When a system is moving, it has a velocity, it has some kinetic energy associated with it. The other type of energy is called potential. And this energy does not depend on velocity at all. An object cannot move and still have some energy built into it. This energy generally is about its position. So where an object is in relation to other things could affect how much energy it has. So for instance, think about it like this. We have, you're holding a marker in your hand. Okay? Then hold the marker above your head. So now it's a lot higher than it was before. Believe it or not, the marker above your head has more energy than the marker in your hand below. Because of its position relative to the ground. And in fact, this is a special kind of potential energy called gravitational. And that type of potential energy says the higher you are above the surface, the more energy you have, because gravity is trying to bring you back down again. So that's one type, say potential energy for gravity. I'll give you the equation, but we're not going to need it right now. We're going to need it in the next lecture. It goes like this: m times g times h, where of course m is mass, g is gravity, 9.8, and h is the height. How far above the ground are you? The higher you are, the more energy you have because of gravity. If you look at the units here, m is kilograms. G, that's an acceleration. Remember, gravity is an acceleration. So that's meters per second squared. And h is in meters, height. So that's kilograms, meters squared per second squared. Again, which of course is joules. So good, the equation works. We knew energy had to have units of joules because kinetic energy has units of joules. Well, potential energy is energy. It's just a different type. And so obviously it should have the same units, and of course it does. But this is only one type of potential energy. Unlike kinetic, kinetic only has one equation, 1/2 mv squared. That's it. No matter what the object is, what the system is, if it's moving, if it has a velocity, you can calculate its kinetic energy. There it is. Potential energy is more complicated because there are many different types. Gravitational is one type, but there's another. There's a potential energy of a spring. Think about this. When you have a spring, let's say, you have a spring. If you compress the spring, you push it, you squeeze it together, it's not easy to do. You're actually having to apply a force to push it together. And as you're holding it together, compressed, it's wanting to release. So you're having to hold it from releasing. That's a storage of this potential energy in the spring. As soon as you release it, as soon as you let it go, that spring pops back out again. So as you're compressing the spring, you're storing some energy into the system. It is a potential energy. It has the potential to be used. So this type of potential energy is 1/2 k x squared, where k is something called a spring constant. It just tells you how stiff is the spring or how loose is the spring. How easy is it to compress? Spring constant. And x is how much the spring is compressed or stretched, because it works the other too. If you take a spring and you stretch it, it wants to come back together again. And so you can see here's another energy that relates to its position, how much it's compressed or how much it's spring. It's a distance, it's a position type thing, rather than the spring moving around fast, with some velocity. And there are others. There's, you have electric charges, and the closer two positive charges are together, the more they want to repel each other. So there's a potential energy about electricity and all sorts of stuff. These are the ones we're going to concentrate in this class, gravity and spring. And like I said, don't worry about memorizing them now. I'm just introducing them. For now, what's important, what's critical, is this kinetic energy. That's what we're going to be making use of in this particular lecture. So how are we going to make use of it? Well, notice you apply work. You're applying a force to an object. We know from Newton's second law, F equals ma, forces give rise to accelerations. That means forces give rise to changes in the velocity, right? You apply a force, you're changing its speed. Maybe you had a box on the ground just sitting there, you start pushing on it, now it's moving with a velocity. You changed its velocity, you gave it an acceleration. Or box is sliding towards you, you push in the opposite direction, you start slowing it down to stop it. So we already know that forces give rise to accelerations, and we know work is a measure of the force you're applying, because it's force times distance. So obviously work must have something to do with an acceleration. When you apply work to an object, you must be changing its speed, because the implication of work is force. And what do we know about changes in speed relative to this energy stuff? Well, kinetic energy is the velocity, or velocity squared. So if we're changing the speed, if we're changing the velocity by doing work, we must be changing the energy. And in fact, that's what this theorem says. Work is equal to the change in the kinetic energy of the system. Very easy. Nice little bitty equation here. To write it out a little bit more, when you apply work to a system, you change the kinetic energy, which means you have final kinetic energy minus initial kinetic energy, which is 1/2 mv final squared minus 1/2 mv initial squared. And this is our equation. Now what we're going to be able to do is, for all the problems we've asked in the past about work, we can ask a new question, a part B, let's say. So if we remember, take for example, the question where we had box on the table, mass 10 kilograms, we push with a force of 100 newtons to the right, and the box slides a distance of 5 meters. We said calculate the work. But now we could ask a second question, which is, how fast will the block be moving after it has slid the 5 meters? Okay, so part A, we did this before. Part A says work is equal to force times distance. And we asked the question, what's the direction of motion for this problem? The box is on a nice horizontal surface. It's moving to the right, so it's moving in the x direction. That means all I need are x forces. What are all the forces in the x direction here? Well, I've got the 100 moving to the right times the distance it moves to the right, which is 5. And there are no other x forces. So there's only one work I have to calculate, and I get 500 joules. So that's what we did last time. Now, we have a second question. Think about it. You're pushing on the box. It's accelerating, getting faster and faster because you keep pushing. And then after it slid 5 meters, someone has a little radar gun and measures how fast is a block moving at that point. Well, to calculate it, we say, this is a problem. We're dealing with forces, and we want to know how the velocity is changing. That's a work-energy theorem problem. And a work-energy theorem says work is equal to the change in the kinetic energy. By the way, when I write, a lot of times you're going to see me just write K, capital K for kinetic energy instead of KE, because I prefer, single variables instead of two-letter variables. But just know K means kinetic energy. So if you want to write KE, that's fine, but I won't always write KE. But if you see capital K, it means kinetic energy, unless something comes up, and I'll let you know whenever that happens. But for now, capital K means kinetic energy. So there's my equation. In order to solve it, of course, I need how much work is done, and I need to know about its initial velocity, because I'm looking for the final velocity. How fast is it moving at the end, 5 meter mark? Well, in a problem, if the initial velocity is not given, then just assume the block was initially at rest. The block was just sitting there on the table, then someone started pushing on it. So we're going to say the initial velocity is 0. So we have work, which we already calculated is 500, is equal to 1/2 m v final squared minus 1/2 m v initial squared. But v initial squared is 0 because we're assuming it started at rest. If it didn't start at rest, then I would have had to tell you in the problem the block was initially moving at 2 meters per second. Then this force is applied, blah, blah, blah. Here, I don't mention anything about the initial, so pretend it was at rest. So the whole initial thing goes away, and we have 500 is 1/2 the mass of the block, which is 10 kilograms, v final squared. So all we have to do is solve for v final. So I get v final is, 1/2 of 10 is 5. So divide the 5 over to get v final squared by itself. 500 divided by 5. But then that's v final squared. So I have to take the square root of both sides to make it just v final. So I get 500 divided by 5 is 100. Square root of 100 is 10. So how fast will it be moving? It'll be moving 10 meters per second. Now, technically, when I took the square root, there should be a plus or minus sitting there. So the answer could be plus 10 or minus 10. But we already know the block's sliding to the right, so obviously it has to be a positive velocity because it's going to the right. If the block were moving to the left, it could be negative. So that's this work energy theorem. That's all there is to it. We already know how to calculate the work of a system. Once we know how to calculate the work, we set that equal to the kinetic energy. Or more specifically, the change in the kinetic energy. But if the initial state was 0, if the block was at rest initially, then the final kinetic energy is its kinetic energy. So let's look at another example. Let's look at the example of, let's do the crate with a helicopter. Let's say the crate has a mass of 1,000 kilograms. The helicopter is accelerating upward with an acceleration of 5 meters per second squared. And the helicopter lifts the crate a distance of 100 meters. Okay. So that's our situation. We have a crate. I'll write out the question just so that you don't have to just rely on the picture. You can hear the question too. A crate of 1,000 kilograms is lifted 100 meters into the air by a helicopter which is accelerating at 5 meters per second squared. Calculate the work done by the helicopter by gravity and the final velocity of the crate. That is, what's the velocity of the crate when it reaches the 100-meter mark? All right, so this is a nice complex question. This is one of the harder versions of this type of question. So, in order to do this, of course, we're talking about work, the work-energy theorem, but in order to do the work, we need to know about the force. I don't know what force is applied here. So the very first step to being able to calculate the work is to figure out what force is being applied to the crate. So let's look at the crate. What forces are on it? I've got gravity, mg, pulling it down. And I've got the tension in the rope pulling it up. Those are the only two forces acting on my crate. So I could do F equals ma and say we're looking in the y direction because the crate's moving upwards. What are all the forces in the y direction? Minus mg down. Tension is plus tension up. Must be equal to the mass of the crate times its acceleration, which in this case is 5 upwards. Now what do I want? I'm trying to figure out the tension, because the tension tells me how much force is applied to my crate. That's what's lifting the crate, the tension. So let's solve this equation for T. You bring the minus mg to the other side, it becomes plus mg plus 5 times m. Plugging in our numbers, what's the mass of the crate? 1,000 times 9.8 plus 5 times the mass of the crate, 1,000. So we get 9,800 plus 5,000. So we have 14,800 newtons. So that's the tension. That's the force which is lifting up on our crate. All right. Now that the background calculation is done, we can start. Part A. What's the work done by the helicopter? Well, work is force times distance. What's the direction of motion? The box is being lifted up, so it's the positive y direction. So how much of the force, which is tension, how much of the force is in the y direction? And remember, I'm only looking at the work done by the helicopter, not the total work done, not the work done in the y direction, but just the work done by the helicopter. The only thing the helicopter is doing is giving the tension. All right, so how much force, how much of my tension is in the y direction? The whole thing. It's being lifted straight up. It's a y-directional force. So the whole force is in the y direction. How far does my block travel in the y direction? 100 meters. So what's the work done? 14,800,000. There's our commas. joules. So 1,480,000 joules. A whole lot of work is being done here. That's how much work the helicopter does to my box. Part B says, what's the work being done by gravity? Gravity is a force acting on the object, and it might be doing work. Maybe it's not. If we look at the previous example, over here, there was still gravity, mg. But notice, for this system, the box is moving in the x direction, so all I cared about were x forces. Gravity is a y force. So gravity cannot be doing work here. However, here, because my box is moving in the y direction, and gravity is a y force, then obviously gravity can be doing work. So how much work does it do? Well, work is force times distance. We say for the gravitational force, how much of the gravitational force is in the y direction? Well, again, the whole thing. It's all in the y direction, so it's mg. That's the force. How far does it go? 100 meters. However, notice my box is being lifted upwards, so it's traveling up 100 meters. But gravity is a force which is pointing down. Since they're opposite directions, this is a negative work. Okay, so negative m, that's the mass, 1,000 kilograms. G, 9.8. 9.8. And the distance, 100. So what's the answer? Minus 98000 joules. All right, so pretty nice. How much work is done by gravity? Negative 980,000 joules. Again, it's negative because the force due to gravity is opposite to the direction. The direction is up, gravity was down. So work is negative. In the first one, the helicopter is lifting up, and the object moves up. Since they're both in the same direction, he was a positive work. All right, so pretty nice. Work done by helicopter, pretty easy. What's the force done by the helicopter? Well, unfortunately, we had to calculate it, but that wasn't so bad. That's what was in green. The tension. Once we know the force done by the helicopter, the tension, we multiply it by the distance. We got the work done by him. Gravity, same thing. How much force is gravity? mg. How much of that is in a direction of motion? The whole thing. It's a y force. All right? So mg times 100, but negative because gravity is opposite to the direction of motion in this problem. Let's say the helicopter was moving down, so the crate was falling. Well, the crate fell 100 meters, and gravity's pulling down, then they're in the same direction, so it would have been a positive. So remember, don't think, because it's gravity, it must be negative or anything like that. It's all about the directions. Is the force in the same direction as the distance or opposite direction? All right, what about part C? We want to know how fast will this crate be moving when it reaches this 100-meter mark? Well, that's where the work energy theorem comes in. Work energy theorem allows me to relate how much work is being done to an object with its velocity, its speed. So I'm going to say work is equal to change in kinetic. Again, in this problem, I wasn't told about its initial velocity. So I'm assuming the crate was just sitting on the ground, and then the helicopter started lifting it off the ground. So it started with no initial velocity. So all I need is the final stuff. So I don't need to worry about minus initial. Minus initial is just 0. So here I need the work done on the crate on the left and 1/2 mv squared on the right. Well, the work, what work do I put? Do I put the work done by the helicopter? Do I put the work done by gravity? Do I add them together, the total work? Which work is the correct work for this calculation? And it turns out that it's the total work. All the works added together, acting on the system, gives you the change in the kinetic. So this is total work. Okay, well, what's the total work? It's just adding up all the works. So I have the work done by the helicopter plus the work done by gravity is 1/2 mv squared. All right, so 1480000 plus negative 980000 equals 1/2 the mass 1000 times v squared. All right, so 1,480,000 minus 980,000, that gives me 500,000 equals 1/2 of 1,000 is 500 v squared. So v is, of course, 500,000 over 500. And then to get rid of the square, I take the square root. So, stick it in your calculator, you get 31.6. And there we go. So again, one of the more complicated work energy theorem problems. And what makes this complicated is the green part. You had to calculate the force. It wasn't just given to you. But that's not complicated because that's just what we did when we did Newton's laws. You know, find the force, F equals ma. We calculated the tension. The tension is the force acting on the crate. So you do that first. Once you have it, part A, B, and C obviously are not that complicated. Part A, how much work is done by the helicopter? Well, the helicopter is the thing given the tension. So it's really saying how much work is done by the tension. Well, the helicopter is giving the tension. So you say, what's the direction of motion? The box is moving up, so it's positive y direction. How much of the tension is in the y direction? In this case, it's the whole thing. So we take the tension times the distance. It's positive because the tension is up and the distance is up, so they're in the same direction. And we get the work done by the tension or the work done by the helicopter. Part B, work done by gravity. Same thing, force times distance. What's the direction of motion? Positive y direction. How much of gravity is in the y direction? All of it. Gravity is a y directional force. So the force, mg, times the distance, 100. In this case, it's negative because gravity is down, the distance is up. They're opposites, so it's negative. Calculate it out. I now have the work done by gravity. It happens to be negative, but whatever, that's it. Now part C. After the helicopter, as the helicopter is lifting this crate up, once it reaches the 100-meter mark, how fast is it going? Well, now you're relating work stuff with velocity stuff. So that means we're doing work energy theorem. All right, work energy theorem says the work done on a system is the change in its kinetic energy. So work is equal to final kinetic minus initial kinetic. Well, in this case, I'm assuming initial kinetic is 0 because I was not specifically told the initial velocity. Now, it's important to keep in mind you will get some questions where there is an initial velocity. All that means is it's 1/2 mv final squared minus 1/2 mv initial squared. But you know the initial, so that's just a number. Here, however, we don't have initial, so it's just 0. So I have work is equal to 1/2 mv squared. And I'm looking for v. What work do I use? You always use the total work. If you're doing a work energy theorem, it's the total work that matters. So that just means however many works there are in your problem, you add them all up. In this case, there's only 2, because there's only 2 forces. The helicopter is one, gravity is the other. You add them up. In this case, one of them happens to be negative, so it's really subtracting. But it's work plus work plus work. So you add up the works together, you get a total work. The other side, 1/2 mv squared. Bring everything to one side, v by itself. Take the square root, and you have how fast this block will be moving. So that's work energy theorem. All problems will be done like this. And in fact, what you see if you have been working on the practice problems is every single problem I had where you had to calculate work, I always gave a part B that says how fast will the object be moving. So there's no really new problems I'm asking you for doing work energy theorem. It's the same exact stories, the same problems. It's just now I can ask, calculate the work, calculate the total work, whatever, but also I can ask for its velocity. So you're going to go back to all the practice problems you worked and now solve a part B. Use work energy theorem to find the final velocity or whatever. So that's the good news. The good news is, even though I've introduced a new idea, there's not really new problems. It's the same problems, just calculating something new. So I hope this was informative. As always, if you have any questions, let me know. And until next time.